Hello, my name is Laurent van Groningen. I'm an enterprise energy system architect at Alliander. And in this video, we will look at resilience operational design and what needs to be in place to prevent a single failure or security issue causing a system collapse. For that, we have two learning objectives today. First, to understand why resilient operational design is important, so we can keep capacity available at all times. Secondly, to understand that the responsibility is no longer within the grid operation only. Today, many different actors influence the safety and reliability of the energy system. To design resilience, we first need to understand how control actually works across the different layers of the system. So let's have a look at the different types of controls. But first of all, we often use the word control as it always guarantees an outcome. But that's not always true. If communication fails or a wire is broken, the command might simply not be executed. So, see control at all layers, but designed or intended differently. Let's then go into the layers. First, we look at the actuation options available on the lower layers, like assets and grid management. We act on assets that are owned or directly accessible by the DSO, so the former grid operators. Here we have real direct control. On the upper layers, we act on the customer or market assets that we don't own. In that case, we don't truly control them. We only rely on them to respond. Now, let's look at the dynamics of those layers. At the market layer, control starts with a negotiation and resulting in a transaction. After that, the execution is outside our hands. We simply trust that it happens. At the capacity layer, we send operational requests, for example, curtailment set points. But again, these devices are not owned by us. Once the set point is sent, execution depends on the customer side. In grid management, we control the grid directly. For example, switching possibilities in the network. Here the commands are executed on our own infrastructure. And at the asset level, protection and voltage control act automatically. Set points immediately lead to actions in real time. These layers also differ in timescale. Market actions happen day ahead of time, in the intraday period or close to real time. Capacity management works from the planning phase down to intraday. Grid control is reactive. That is, we control the grid only when something goes wrong. And protection acts instantly in real time. For example, by automatically switching off assets and thereby restoring the energy balance. However, during large external disturbances, many protection devices can operate simultaneously across the grid. So in summary, the higher layers, like market management, are more stochastic. In these cases, we hope actions are executed. In the lower layers, close to the assets, we are much more deterministic and predictable. But even there, nothing is 100% guaranteed. Now, what type of measures are needed for a resilient design? Here we give an overview of the main ones. First, cyber and telecom security. This is the foundation of everything, at least being connected, because without reliable communication, few other control actions will work. Secondly, scheduled and up-to-date set points in distributed devices. If communication fails, real-time control is no longer possible. By sending schedules in advance, we still get predictable behavior. Then, grid falling and grid forming capabilities. All controllable units should adopt their behavior, follow the grid voltage, but also actively support grid during disturbances, for example by continuing to shortcut current or stabilizing voltage. These are examples of clear requirements for generators and controllable units. And since we don't own these assets, we depend on the rules and the specifications to make sure that their behavior supports system resilience. For DSO-owned assets, we use protection systems and also the thermal resistance of components. Cables and switches are designed for worst-case conditions, which sometimes mean we can safely use additional capacity, for example, during colder periods. This enables us to avoid using high-impact security measures if not necessarily needed. Manual control is also important. Even without automation, operators must still be able to switch and operate assets manually if needed. Next are operational processes, such as releasing capacity when it's safe. The closer to the real time, the better we can predict the situation and use the grid more efficiently. So to recap, resilience is essential for operating capacity and flexibility management. We cannot rely on a single measure. Instead, we need a combination of measures both in technology and processes. We must act in advance because there are no options left, only trusting on reactive real-time actions. Beside this, it is essential to understand that the DSO does not own or operate customers or market assets. Combined with a higher number of controls of those assets, these controls are more stochastic, but essential. Here we depend on clear requirements and agreements. So overall, resilience must be designed into the system from the start. Thank you for watching.